Greetings to everybody. I would like to, so nice to see you, Bestin. So
Hello.
let me introduce Bestin James, and he's now in Warsaw, in Centrum for Theoretical Studies, led by Professor Agnieszka Janiuk. And he will be speaking about harm code and how his research. And since this lecture is supported by European Union, we have the flags on the screen. So just like in case, you know, this is European Union, this is Czech Republic. So Bestin, if you wish, you can start. You can start to share screen. Actually, the lecture is recorded already, so you can start. The floor is yours.
Thank you very much, Martin, for the introduction and for inviting me for this talk. 1 second, I will share the screen now. I hope it's visible.
Yeah, it is.
Okay. So, hello everyone. My name is Bestin James, and I'm a PhD student at the Center for Theoretical Physics in Warsaw. Like Martin said, I'm working with Professor Agnieszka Janiuk, and here are other people I collaborate with. So I will start. I will today talk about using harm code for simulating creating black hole environments. And actually, Martin asked me to give like the basic introduction. So I tried to keep this like in a simple way. So I will start with this astrophysical motivation, why we are doing all this simulations, like GRMHD simulations. So the first destination is gamma ray bursts. So gamma ray bursts are the most energetic events observed in our universe in terms of electromagnetic emission, releasing a total energy of up to 10 to 54 Earths. Like if we have different models for calculating this emission. So if we assume an isotropic emission, we get such high energies. Otherwise, like maybe 2-3 orders of magnitude less, but still it's the highest observed energetic electromagnetic events observed in the universe. And basically we classify gamma ray bursts based on their duration as short and long GRBs. It's some conventional classification, and this division is at 2 seconds, and which are shorter than 2 seconds, and which has variability in some few milliseconds are often classified as short GRBs. And this is an example light curve for a short GRB, which has a variability or a flash in some millisecond scale. Then there are long GRBs which vary over a few seconds. And typically we attribute 2 different mechanisms for these 2 classes of GRBs. And these short GRBs are often connected with a merger of 2 compact objects, usually a black hole and a neutron star, or binary neutron star merger. And at the end of this merger, we expect a black hole to form in both cases, like just to end up in one black hole and some accreting material around it. And the second scenario, which is considered for the long GRBs, are this collapse of a massive star. And in this case also, after this collapse to central black hole, there will be some material left around it with some angular momentum probably. So then it also results in some accretion disk around a black hole. So both of the scenarios result in some accretion disk around a black hole. And then on very huge, like large scales, we have active galactic nuclei. And also as we know, nowadays, it's our understanding is like every galaxy has some supermassive black hole at its center. And this nucleus can be, and this center of this active galaxies are often called active galactic nuclei, and this nuclei can be either weakly active, which means there isn't much electromagnetic emission in all wavelengths, but like for example our own galactic center Sagittarius A star, or then there are like very strongly active galaxies like quasars, which we observe like some relativistic jets expanding from its center. And the level of activity probably depends on the amount of matter accreted by the black hole and how it varies with time. And so this radiation we observe from the vicinity of the central black hole provides us information about this center of this active galactic nuclei. Otherwise, it's very distant from us, and usually it's especially unresolved in other kinds of observations. So despite of this general understanding, we don't have a clear picture about clear understanding about this kind of observations also in terms of their observed emission spectra and this time variability. So this is a very recent radio image of our nearby M87 galaxy, which is also an active, which also has an active nuclei, and it shows it's some millimeter wavelength image, and it shows this accreting material around a supermassive object, and this also jet in one single image. And so here also this disk accretion onto black hole is considered as the driving mechanism. So here are this example light curves again for the GRBs, and so here we can see like sub-second variabilities in this GRB light curves, which I showed earlier, like this another observation. And here are this light curves for an active galactic nuclei Markarian 501. And here we can observe variability in terms of few hours in this inset, like if we consider this smaller region or like a range. And so then in this both kind of objects, we observe like if both kind in the sense like not all active galactic nuclei, but quasars, and in GRBs we observe this radiation in the form of jets. So I explain what are these relativistic jets. They are beams of ionized matter or radiation accelerated close to the speed of light, and it is a very common phenomena in many accreting black hole objects, and in other kinds of sources also, like neutron star. And they are, like I explained now, they are observed at a different mass scales of the black hole. For example, in case of GRBs, they are in stellar mass black holes. And then in the case of supermassive black holes, these masses can be even higher than this, even like 10 to 11 solar masses in terms in the case of active galactic nuclei. So this is some schematic which shows the formation of the jets. So, and I will explain. So usually we attribute the formation of jets to the presence of magnetic fields in such in the plasma in such kinds of environments. And so GRBs and blazars is a class of active galactic nuclei which is pointed towards us, this jet. So they are observed as relativistic jets pointing towards our line of sight. For this GRBs, we don't see this extended jet structure. We only see this flash of light which is directed towards us. And so both of these jets kinds of jets are often Poynting dominated, which means so mostly dominated by radiation, and we have some mechanism which explains the power of the jets observed from such sources. So in this, it's called this Blandford-Snag process, and it's basically it's some very simplified schematic. Here, this magnetic field lines are frozen in the plasma around the accretion disk, and when the black hole rotates, this field lines also rotates along with it, and then it gets twisted, and this so then matter is accelerated along with it and pushed upward. So this is a very simplified explanation of this Blandford-Snag process. And here, so the power observed in Blandford-Snag process is often is proportional to the flux on the black hole horizon, which we can quantify this way, and also to the rotation of the black hole. This dimension, the curve parameter. So we say that this properties of the central engine, which is in the black hole and the accretion disk, can affect the properties of the jet also. So this is another reason we are focused in this GRMHD simulations to study the properties of these jets observed. So let me start with this accretion processes we are studying. So to start with, we can consider some the simplest case, or the simple model, like we have some central gravitating object, and then there is some matter distribution around it. So for the simplest case, we have like some spherical distribution of matter without any rotation. So often in many cases, we will have rotation and it will go to the disk regime. So here, so for the so we often consider this hydrodynamical description, like fluid description of matter, to model such environments. And so in such case, in astrophysical, many astrophysical cases, the accreting matter is not very dense, and the matter is very highly ionized, and they have this collision interactions in terms of, we can quantify in terms of Coulomb interactions. So these interactions are very frequent, and so the flow can be characterized by density, pressure, and temperature. And this hydrodynamical approach is sufficient for such systems. So the simplest case is, like I described, this uniform accretion, spherical accretion to a central gravitating object. So in 1952, Bondi found some solution for such a flow by solving this hydrodynamic equations, continuity, energy conservation, momentum conservation of the gas. And so in this case, there is this assumption of steady accretion also to the not like steady in time to the central object. So spherical symmetry, steady state, and gas at rest at infinity, like far from the central object. So in this solution, after solving these equations, he found that there is some particular radius, like above which the gas is essentially not very affected by this central object, and below which the gas dynamics is detected by the central object. And then there is, and we can understand from this causality that, like, so if gas is at rest at infinity, then it will be accelerated as it approaches the central object. Then there will be some point, like where it reaches the speed higher than the sound speed in this medium. Sound speed means like it's the speed at which the pressure differences propagate in a fluid. So the sound here, it's like the sound speed at infinity is given by the pressure at infinity and density, and this gamma for the gas. So he calculated the value for the Bondi radius, which gives such effects as this Gm over sound speed at infinity square. And now we move to accretion disk. So accretion disks are flattened objects which is made of rapidly rotating gas, which slowly spirals into a central gravitating body. Here, this image, just some representative image. It's the X-ray image of the Crab nebula from Chandra Observatory. Here we can see some disk-like structure. It's basically not a black hole, but a pulsar, like some neutron star, accreting the matter around it. So prior, like in difference, comparing to this previous case, here the matter is in the form of a disk. So it's the main reason that, like in most astrophysical scenarios, matter often will have some angular momentum also. So like the steady spherically symmetric accretion is not possible in such scenarios. Then if it has some rotation, and then due to the collision of matter in this region also, it will finally settle down to some form of a disk. So this rotation and this collision of matter results in a, for this angular momentum conservation, it results in some disk around a central object. So like I explained, this gravitational energy of the infalling matter extracted from this accretion disk in powers in the sense like it produces this electromagnetic radiation we observe from sources like active galactic nuclei, protoplanetary disk, and gamma ray burst, and also stellar binaries, some of them. So the high angular momentum of the material. So when we consider the accretion onto compact objects, the main question is like how the angular momentum is transported outwards, because like when we know that like from simple Newtonian dynamics, like when there is a central object and there is some centripetal force around an object, and when it's in some orbit around it, it will stay in this orbit and it won't move inwards. So we need to understand like how this angular momentum is transported outwards in this disk. So people assume different mechanisms like stresses due to turbulence in the disk, then viscosity in the disk, then this action of magnetic fields in the disk. So different mechanisms are considered for the transport of angular momentum in various systems. So initially people assume that this usual molecular viscosity could be a candidate, but it became apparent very soon that it's not enough. Like this usual molecular viscosity is not enough, like hugely insufficient to explain the luminosities we observe from accreting sources at all scales. So then there were different other mechanisms were considered to explain this transport of angular momentum, but it was unclear for some decades, like what is the exact mechanism. So people considered magnetic stresses and self-gravity in the disk and several other mechanisms. So when it was really unclear, but there were some ideas. But so to explain the properties in 1973, Shakur and Sunyaev came up with some idea of some effective viscosity parameter which drives the angular momentum transport in the disk. So they assume like if we can assume some effective viscosity due to all these kind of mechanisms, then we can explain this angular momentum transport. So it's the basic assumption is like they assume this hydrodynamical stress tensor is of this form, where rho is the gas density and V is the kinematic viscosity, and V phi is the azimuthal component of the velocity in the disk. Then they propose that it will be of such form. This stress hydrodynamic stress tensor will be proportional to pressure, and there will be some constant here which for a disk, and it can have values between like higher than 0 and less than 1. And in realistic disk, this alpha has some values like 0.1 to 0.3. So it's some like actually effective viscosity of different mechanisms which acts in the disk. So in realistic scenarios, we assume that one of the main reasons for the this stress is very likely the turbulences driven by magnetorotational instability. It is a mechanism we found to explain the turbulences developed in weakly magnetized accretion flows. So so it was actually originally described by Velikov in 1959, then Chandrasekhar's in 1961 in his book like Hydromagnetic Instabilities, but its importance was not very clearly understood. So they considered like if in some differentially rotating fluid with weakly magnetized differentially rotating fluid, Chandrasekhar explained like there will be some instabilities developed due to the magnetic field action, but its importance to accretion disk was as an angular momentum transporting mechanism was recognized by Balbus and Hawley in 1991. And in this paper, this 1998, they have some good review paper, like how they explain all these mechanisms. So I will try to explain this MRI with a simple toy model. So if let's consider that this rotation is like counterclockwise in this diagram, and this blue and red circles are two fluid elements in this disk, and they are connected by some spring orbiting around a central mass. And in this real scenario, this spring stands for this magnetic field. Then if we assume that this rotation in this direction, then when it rotates and so they are in nearby Keplerian orbits. So when it rotates this outer element, and consider that it's differentially rotating, so then this inner element will be pulled backward, and this outer element will be pushed forward as it moves. And then this way, this inner element loses its angular momentum, and this outer element gains some angular momentum. So this inner fluid element will move further inwards, and this outer element will move further outwards, and basically this angular momentum is transported outwards as this rotation proceeds. So in this case of realistic scenario, in highly conductive plasmas, this magnetic field acts as the spring and giving rise to this magnetorotational instability. And so now I hope I have described some basics which we need to know. So now I move to the harm code. So it is I know that from Martin that you have already have some talks describing the harm code already, but I just describe the basic equations here. So harm is it stands for this high accuracy relativistic magnetohydrodynamics code, and it's originally developed by these people, Gami et al., and their paper describes this basics of the code, and it's a conservative shock capturing scheme for evolving the equations of GRMHD. So basically the code solves this three equations, like this continuity equation, energy momentum conservation equation, and this for the fluid part, and then for induction equation for finding the evolution of magnetic field also. So the stress tensor is in general contains fluid part and electromagnetic part, and the fluid part is given by this expression. Here U is the internal energy of the gas, U mu is the for velocity of the gas, and this electromagnetic part is given by this expression. Here B mu is the magnetic for vector. It's assumed for convenience. And it depends on this Faraday tensor. So in force-free approximation, this holds, and this code follows the unit convention, like this natural convention, like this gravitational constant is the same as speed of light, and the central mass of the black hole as 1. And now I describe some Fidocial model we use in like where we start usually the simulations. It's called Fishbone-Moncrief disk. I also assume that you are familiar with this. So it's some hydrodynamical solution. This Fishbone-Moncrief disk is some hydrodynamical solution. It's from 1976 for a pressure equilibrium torus, like stationary torus in Kerr geometry. So this solution like stays stationary in time and it does not evolve. And the particular feature is that for this disk is that it has a constant angular momentum distribution along the torus, and here it's given by this value. And here L is the specific angular momentum and omega is the orbital frequency, which is given by this expression. And then there is some expression for enthalpy also, which we calculate in the code. So in our code, when we describe this solution in Ham code, we parameterize this solution by the inner radius of the disk, which is given by this variable Rin, and then this radius of maximum pressure, gas pressure in the disk. I will also describe when we discuss the code, these values. And then, so I note that like this disk solution is some stationary solution, and if we just put this in the code, it will stay stationary in time. Other than maybe some numerical artifacts, some effects can change like slightly this disk solution. Otherwise, it will stay stationary in time. So we need some magnetic field also, and so we put some magnetic field along with the disk, which produces this magnetorotational instability, like I told. So, so we prescribe the form of magnetic field by providing the form of vector potential for the shape of geometry we want. For usually we assume in 2D, we usually don't evolve we only consider the evolution in the R and theta directions, and we only consider just one cell in the 5 azimuthal directions. So in such 2D cases, we usually assume this poloidal fields, which has dependence B on this only 2 components, basically this BR and B theta, and this phi component of this azimuthal component of the magnetic field is often assumed 0. So in such a case, the only component of the vector potential we will have will be this phi component of the vector potential. And in this symbol models we consider, we put such a field that these field lines follow the contours of the disk density. So in such a field will have the vector potential of the form this. Here rho bar is some average of the density in each cells, and this is the maximum pressure in the disk, and this is some offset value we choose to confine the field lines within the disk. Like we can change in the code, we use this like 0.2. We can change this value to make our field lines how big in the disk, like how how much region it exists. And many other configurations we can use. For example, dipole field or an asymptotically uniform field, like straight lines aligned with the rotation axis of the black hole. It's given by this Wald solution. So it depends what we want to simulate. So this paper by Martin has few different field geometries. He has studied its effect and how it evolves in time. So you can check this, it's in archive. So if you check, you can see the different forms of vector potential which we can use to produce this field geometries and how it evolves with time also. So we assume now we have some geometry for the field. So now we have to set how strong this magnetic field is. So for this, we use this parameter, plasma beta parameter, which is defined as the ratio of gas pressure to magnetic pressure. So it's like if we use like symbol gamma law for the gas, then we have the expression for the gas pressure by this way, gamma minus 1 times the internal energy of the gas by, this is magnetic pressure B square by 2. So then I just say another example for this configuration of the magnetic field, which is very similar, which also follows the isoconducive of disk density, but we also put some dependence on the radius. So such a field configuration is often used for producing this magnetically arrested accretion disk state, which I will also describe in some minutes. So here, if we put such a dependence on the radius, this field lines will be or the geometry of the field will be much bigger, like, or it will be much bigger than the disk, like this one. So it will thread along the entire geometry of the disk, or even outside the disk. So for such a field, it will with time it will bring in more magnetic flux to the horizon when we run it for a longer time. So it's just another example for another field geometry we often use. And now I want to describe like how we convert this result. Now I told already that this harm code works in such units like this, G equal to C equal to M equal to 1. So in such case, our results are in these units, like or the length we have, like this radius in, for example, the radius of the disk, like here we did describe here this R in, R max, or such length will be in these units, like this GM over C square, like gravitational radii. And this time and the time units in the code will also be in units of this black hole mass, because we have this G and C as 1 and M as 1 as well. So the length units will be in units of black hole mass, and the time units will also be in units of black hole mass. So, but now if we want to convert this to physical units, then we have to assume, like, we have to first like consider like what kind of system we are considering, if it's gamma ray bursts or active galactic nuclei, something like this. So for gamma ray bursts, we have like stellar mass black holes. So for example, here we will, to convert it to physical units, here we will assume like some 3 solar mass or something like this for short gamma ray bursts, like for time also. And for if we are considering this active galactic nuclei, then we have this order of like 10 to 6 solar masses here. Then we can convert this length and time units. So basically this results from this harm code is scalable. We can scale it according to the black hole mass. Now, for this disk density, then we have to assume one more arbitrary scaling for the disk. Here we assume some raw unit, basically some density unit. And for this unit, we have to assume some arbitrary mass scaling in the disk. So then it's also depends on this environment we are considering. For example, for the case of gamma ray based disk, because this disk density will be different in the case of gamma ray burst, this disk will be comparatively very dense, and in the case of active galactic nuclei, this disk around this black hole is like often very not very dense, like it's more not dense. So this mass scale in the disk determines this density unit we are using. So for example, for the case of gamma ray burst, we consider like such unit, like 1.5 times 10 to minus 5 solar masses in this environment. Then this density unit will give some appropriate physical density in the case of gamma ray burst, if we use such value. So for more details, like more examples of this calculation is in this paper by Professor Yanuk and me, like for the case of gamma ray burst as well as active galactic nuclei. She explains like why this active galactic nuclei, in such cases, we are not sure like what scale to use actually, because we are not sure of this matter composition or this density there very clearly. Now I will just describe also so my last project here very briefly, which was also published in last year. So I used this harm code to model this jet properties of gamma ray burst by considering the so-called magnetically arrested accretion disks. So I will explain what just some introduction to this magnetically arrested accretion disk. So it is characterized by the accumulation of colloidal magnetic flux near to the very close to the black hole horizon. It was actually initially described by this Igumenchev and such Narayan, such people in this early 2000s, the field. So basically when the accretion happens, it brings in more, in many realistic systems, it brings in more magnetic flux to the black hole horizon. But this black hole will not take inside this magnetic field because of the no-hair theorem, because it only has this mass and spin components. So this flux will stay near this horizon because of the inward pressure of the gas, and it cannot escape, and it cannot go inside the black hole also. So this flux will thread the black hole horizon, and over time it will develop a considerable amount of some colloidal magnetic flux. And thus, when after some time, this flux will, oppose this accretion. So this accretion will not allow this flux to escape, and this magnetic flux will not allow the accretion to proceed in like very fast manner. So then the velocity of the gas in such regions threaded by such high magnetic flux will be very much smaller than this free fall velocity of the gas. So then this gas has to find some other way to go in pushing towards the black hole. So it often happens through magnetic reconnections, like because of the magnetic flux more brought in by the matter, and then also some other plasma instability called interchange instability also plays, like we think that it also plays some role in such accretion disks. In this interchange instability is like qualitatively we can say that like this plasma exchanges position through these field lines without modifying the geometry of the field, not so much. So such interchange instabilities and magnetic reconnections play a major role in this driving this magnetically arrested accretion disks. And this is some simulation, like how the matter goes inside through like this azimuthal directions to the black hole. It was one of these initial simulations which considered this magnetically arrested accretion disk by this MŠMT et al. By him. So I considered such a setup for explaining or like trying to explain the properties, jet properties we observe in gamma ray burst. So I explored the magnetically driven accretion and jet variability related to the formation of this magnetically arrested accretion disk state. So I used, like we described, I used two initial conditions for the disk states. So this is like, and this simulation was done in 3D. So I also used some cells in this phi direction, this azimuthal direction, and this is the like this poloidal slice. Like if we cut along this axis, we can. So this is for this first model, which I described this fishbone Moncrief disk, and I also assume like this magnetic field configuration given by such some dependence fifth power of radius, and it follows this contours of disk density, and it's this top view of this configuration. And here it's this there is some problem in this plot. It's because of the some interpolation I used. Actually, this magnetic field is strong only in this region, and this is just some very negligible values. Here also this outside, it was used to this interpolation method I used. And this for this model I considered for this long GRBs, because especially because of the field geometry, because it takes some time. It's like not very long, but still some time to bring, as this accretion proceeds, it takes some time to bring in this field to the horizon. And the second model was described by another equilibrium torus, which is similar to this fishbone Moncrief torus, but there is some difference, is that this angular momentum profile in the disk is not constant, but it depends on such parameter called lambda, which is called von Seipel parameter, because it assumes some cylindrical radius in the disk, and along the cylinders this angular momentum is constant, but with the radius this angular momentum varies in this disk. And I also assume some magnetic field produced by some circular current or circular wire around the black hole. And so here this field is very close, and this current flows to this radius of this pressure maximum of the disk. So here the strongest part of the magnetic field is close to this black hole horizon. And so this, like how to say, as we start the simulation, it's already very magnetized near the horizon, and as it proceeds, it gets fastly very magnetized near to the horizon. And so this embossed magnetic poloidal magnetic fields result in the development of magnetorotational instability in the beginning, because we have some equilibrium disk, and it very fast develops this magnetorotational instability, and this accretion starts, and this accreting plasma brings along with it more poloidal magnetic flux to the black hole horizon. And the magnetic flux accumulated on the black hole horizon can be quantified this way, and it's like integration over this horizon with this poloidal and azimuthal angles. And I just normalize it to the invert mass accretion rate to see like how to compare, like how big it is compared to this invert accretion mass accretion rate. And this is this plot shows this value. So initially this accretion like starts with, because this flux is way, this I explained. No, this plot shows this for this this Chakrabarti model. This model where with this high magnetic field already in the beginning. So this starts this accretion. No, sorry, this flux on the horizon is very high in the beginning itself, and then it falls as this accretion proceeds, and then it starts rising because this plasma brings in more magnetic flux to the horizon, and this accretion still proceeds through this interchange instability, and so it doesn't, how to say, it doesn't go up and up, but it stays in such value because of this plasma goes in, and there is some this magnetic flux thus dilutes, and but still this plasma brings in more magnetic flux, and it stays with such value. For these values we consider, if we have such values higher than this 20 or 15, something like this, then we say that this disk is in this magnetically arrested state. So for my simulation, it stays in this magnetically arrested state for this whole time. So this is another this evolved state just in this beginning of part, where we can see, like, this is some colloidal slice. We can see that this disk is arrested, like this field lines are like highly strong here, this colloidal field lines, and it doesn't allow this plasma to flow in directly. So, but it's this 3D model, so, and it's some colloidal slice, but we can see that this plasma is going into the black hole. So it goes through some other azimuthal direction. It's connected here, this matter, and it goes in. It has to find some other azimuthal direction to go inside, and this accretion somehow proceeds to this, especially this interchange instability developed in this plasma. And then I used like such a parameter. We just call it this jet energy parameter, mu, which is the total plasma flux normalized to the mass flux, like this electromagnetic flux to normalized to the mass flux, to study the variability of the jet emission, because we know that our harm code is some hydrodynamical code, and it doesn't produce any radiation. So light curves we don't have. So in this paper I am describing, I assume that we can consider this parameter, this total plasma energy flux normalized to mass flux, as some substitute for this, how to say, how this variability of this energy emitted occurs. We can, in this paper, they explain why this parameter is useful this way. So, and I assume like some points along this jet direction, and I calculated this value. So this plot shows this 2D distribution, or like along one colloidal slice, this distribution of this value, this mu parameter. And I chose some, and we have like this 3D distribution. So I chose some points along this jet direction, and we have like such angles. So I chose until this region, like some points, and I averaged over this azimuthal direction, like, and to see how it varies with phi component also. And I estimated these values, this mu, and so this mu can provide an estimate of the maximum achievable Lorentz factor at infinity. So it's like some ideal assumption actually. Because we know that this, as this jet moves outwards, it interacts with this, for example, this disk winds, then also with this interstellar medium. But in this model, I couldn't with this harm code, it's not possible to consider all these effects. But I simulate this base of this jet. So if we assume that all this Poynting flux is transformed to this baryon bulk kinetic at infinity, we can consider this this mu parameter, this time average of this mu parameter as the Lorentz factor observed at infinity. So we calculate this mu at 2 chosen locations, and I study its variability, and I estimate this minimum variability time scale, so-called such value. And in this, this was one work I done with Professor Yanyuk and another PhD student in my group. This was this initial work. In this work, we did this calculation initially, and we calculate this variability with time, how this Lorentz factor and this mu parameter varies with time, so that we can see like how this jet power varies with time. And so we can in this first paper we describe like how this variability is connected to this disk structure and this initial disk geometry we assume, and also to this black hole spin, and also to this strength of the magnetic field, how it changes. And in this paper I am describing, I consider particularly this magnetically arrested disk state. So I used this similar method, like I considered some points or some locations, for example, because it's not points in 3D model, but averaged over this phi angle, some locations in this jet direction. And I calculated this time variability. Also, this in 3D models, I calculated this jet structure. It's this same value parameter, but calculated in and sliced over some, or like how to say, flipped over some this YZ plane, so that we can see this distribution of this jet energetics. And here we have this black hole, and this is for these two models I described. This is for this long GRB model, and this for short GRB model. And here we can see that this jet structure is like is asymmetric in this both sides of this axis, and it reaches this higher Lorentz factors or at regions far from this jet axis. It's in this both cases. And so I also have some distribution of this jet structure and how it varies with this polar angle, this theta with time. Also, you can check this paper. And so I summarize. So for more details about this can be found in my paper. Me, Professor Yanyuk, and another postdoc in my group. So I will just summarize. So why we simulate with harm code this accreting black hole environments. The reason is to explain this observed properties of this gamma ray bursts, active galactic nuclei, and this relativistic jets. And still a lot need to be understood in these cases, because we are not sure about this sub-second variability of this gamma ray burst, like how it's produced, like very millisecond scale variability. Also, this jet structure of this gamma ray burst is not very clear, because we are not clearly observing this jet, so we can just make models. So we want to see like how this jet structure and how much is the opening angle for gamma ray burst, for example. Also, we can have to understand how this active galactic nuclei evolves in time. Also, there are so many questions, but I was mostly working in this GRB, so I'm not very expert in this Aegean regime. Then, yes, like I described this equations for, we use this numerical simulation, numerical methods to calculate the time evolution of this accretion flows, because this equations describing this general relativity and this magnetohydrodynamics is not like linear, and no analytical solutions are possible. So we use this numerical tools, and we use this harm code which is an ideal GRMHD scheme for calculating the time evolution of plasma in this geometry we choose. And for modeling this GRB jets and for many other phenomena are made possible with this HAM code. So here I would like to finish my talk, and now I can take questions, and also I can try to just introduce, like just tell the basics of the HAM code. So thank you very much for your attention.